Okay, today we're going to learn about electrochemistry. So when we talk about electrochemistry, we're going to be talking about batteries. And have you ever wondered how these things work? Batteries are just galvanic or voltaic cells. They operate by using the difference in electrical potentials in redox. We simplify this long reduction oxidation by saying redox reactions for different substances. And we can divide chemical cells into two types. Ones that are thermodynamically favorable are called galvanic, voltaic, or electrochemical cells. All three of these words are interchangeable. You'll hear that a lot of times because every year students get confused by the vocabulary. So I want to make sure that you understand all three of these words mean a thermodynamically favorable chemical cell. Okay, the unfavorable cells, those would be the electrolytic cells. So in this video, we're going to talk just about the thermodynamically favorable chemical cells, which are, again, these three types. You should write this down again. In these cells, redox reactions are separated into two distinct containers joined by a wire. Electrons flow through the wire, and a current is created that provides work, or electricity. Electrolytic cells, those are the unfavorable cells. They have only one container for the reaction, and these electrolytic cells will be discussed not in this video, but in the next video. So a voltaic cell, which is the same as a galvanic or an electrochemical cell, will look something like this. Now, there are many different ways that these could look, but in most chemistry texts, you will see something like this. You have a wire that connects two electrodes. This cathode is one of the electrodes, and the anode is the other electrode. In addition, you have something called a salt bridge. The salt bridge could, rather than using a salt bridge, a chemical cell could use just a porous disk to allow ions to flow. And so the salt bridge or this porous disk, they allow ions to flow between the two half cells. All right, now the purpose of a voltaic or a galvanic cell is to convert chemical energy into electrical energy. And there are two electrodes. The electrodes are the pieces of metal. So there's one piece of metal here, and there's another piece of metal here. Many students get very confused. They think the anode and the cathode, those are the electrodes, are the entire half cell. They are not. The anode and the cathode are just these single pieces of metal. Now, the anode is where oxidation occurs. The cathode is where reduction occurs. And a half cell, that terminology, is just one side of the entire chemical cell. So right here, the red side would be a half cell, and the green side would be a half cell. And I already explained a little about the salt bridge. You'll hear some things repeated often because you need to hear these new terms fairly often to try to remember them. Okay, so the salt bridge allows positive and negative ions to flow to each electrode or half cell. And the salt bridge maintains what is called electrical neutrality in the cell. This is because one side of the cell will lose positive charge, the other will gain positive charge, so we need to make sure that we keep each side electrically neutral. The porous disk allows ions to flow, as would the salt bridge. They have the same exact purpose. And a voltmeter is something that is used to measure the voltage of a galvanic cell. And I gave you this unit here. A volt is a joule per coulomb. A coulomb is a charge unit. So a volt is energy, because joules are energy, per unit of charge. So energy per charge is a volt. And 1 mole of electrons has the charge of 96,485 coulombs. That is also known as a Faraday. So when we say a Faraday, we are talking about a mole of electrons. We're actually talking about the charge of a mole of electrons. Now, you'll notice up here, I had the anode and the cathode. So I give these visuals to students. You want to visualize an ox because anode is where oxidation occurs. And you want to envision a red cat because red reduction is where the cathode is. Reduction occurs at the cathode. Okay, You're going to need this chart for homework, for classwork. You'll also be given a chart in the class packet of standard reduction potentials, SRP. One thing that students often forget is that when you are given a chart like this, you are given reduction reactions. That's the word is in there, standard reduction potential. That word reduction is right in there. All of these reactions are reduction reactions. And you'll notice here it says reduction half reactions. That is because just like we have half cells, we also have half reactions. In order to have reduction, you also need to have oxidation. So for a galvanic or voltaic cell, you will have one of these reactions going in the forward direction, and you will have one of these reactions going in the reverse direction. And when we reverse a reduction reaction, that reaction becomes oxidation, because the reverse of reduction is oxidation. And this sign, this is our E0 here, all these values are the half reaction potentials. These are called potentials. If we reverse the reaction, the sign of E0 changes. I'm going to make a quick note to you about something. If we multiply one of these reactions by a number, say I took this first reaction and I multiplied it by 2, the E0 does not actually change, because this volt, notice, remember that's volt, voltage, the units for voltage are energy per charge. Now, energy, if you reverse a reaction, the energy changes. If you reverse a reaction, you still have the same number of coulombs, because the coulombs are based on the charge of the electrons. If I doubled this first reaction, I would double the number of electrons. I would also double the energy. So now the ratio of energy per charge does not change. So if you reverse a reaction, one of these reactions, you have to change the sign of E0 because the energy sign changes. But if you multiply one of these reactions by a number, you do not change E0 because the ratio of energy per charge of electron does not change. Okay, so some more vocabulary now. E-cell, that's called the cell potential. Students will ask me all the time, what is cell potential? What does that mean? It's just the voltage that could be created by a chemical cell. So this little E here, that's called a potential. And then the whole cell potential is when you add the reduction and the oxidation E0s together. So right here, it's equal to E0 reduction plus E0 oxidation. This chart gives you the E0s right there. And that little zero, this 0 right here, it stands for the standard conditions of 25 degrees Celsius. All concentrations are 1 molar and all pressures are 1 atmosphere. And note, remember our reaction quotient from the equilibrium section a few chapters ago. Q is products over reactants for anything that's not a solid or a liquid. And if all reactant and product concentrations and pressures are 1, then Q is 1. Now, E-cell is greater than 0 for all spontaneous or thermodynamically favorable reactions. Delta G is negative, and the cell potential, this is the cell potential right here, the cell potential is positive. All galvanic, voltaic, electrochemical cells are spontaneous or thermodynamically favorable. Those mean the same things. Now, you'll have problems where you have to find the cell potential for galvanic cells. And in order to do that, you have to identify which chemicals are there. You reverse the half reaction that has a more negative or less positive reduction potential, so that the total cell potential will be greater than 0. You'll see this in action in a moment, but you want to have these instructions because students always say, wait, how do I know which reaction to reverse? So this chart that we have here, the standard reduction potentials, has only reduction potentials. So the reversed reactions will all be oxidation reactions. And the more negative reduction half reaction potential is reversed in order to get a positive and spontaneous or thermodynamically favorable overall cell reaction. Since we add the reduction and the oxidation potentials, and we have to reverse one of the two half reactions, you're going to reverse the one that is more negative. So when you add it to the one that was more positive, when you add those two numbers together, you will get a number that is greater than 0, which is what we are looking for galvanic cells. So let's do an example. We're going to look at the copper-zinc galvanic cell. This is a copper-zinc galvanic cell. This side is the zinc half cell. This side is the copper half cell. And we look up the standard potential for zinc and for copper. So you look up here and you're looking for zinc and copper. And let's see, there's the zinc. And notice zinc is on the right side. Zinc is a product. So the reduction reaction has a potential of negative 0.76. And then we look for the copper too. Here it is. This has a cell potential of positive 0.34, which is what I wrote here. So we need to reverse, according to these instructions here, we reverse the half reaction that is more negative, which would be the zinc reaction. The zinc half reaction has a more negative reduction potential, so we reverse the zinc half reaction. And the cell potential will be the oxidation potential for zinc and the reduction potential for the copper 2. And this is just the negative of this number. So we get positive 0.76, because remember, if you reverse the half reaction, then the sign changes. And we need to reverse this one in order to get a positive total E0. We see we do get a positive total E0. Okay, so let's look at the wire. We talked about the wire earlier in this video. The wire allows electrons to flow from one half cell to the other half cell. The anode and the cathode are the solids attached to the wire. So the anode, I talked again about how the anode is literally this piece of metal. This piece of metal and this piece of metal right here would be the anode and the cathode. Now the overall balanced reaction, we have to balance our electrons and our atoms. We would have this copper, where did it go? The copper half reaction, here we go. Here's the copper half reaction, and recall that I reversed this zinc half reaction. And notice I have 2 electrons on the zinc and 2 electrons for the copper, so those are balanced okay. So I'll just reverse the zinc reaction, add it to the copper reaction. The electrons disappear, and this is my overall balanced reaction. If the electrons were not the same, I would have to multiply each half reaction by some number to balance out these electrons, these 2 electrons, and these 2 electrons. But it worked on this one. All right, so in this particular half reaction, in this particular voltaic cell, electrochemical cell, we're going to look at where do the ions move and how do the electrons move. So you want to notice who's being used and who's being created. So we're going to note that the copper 2 ions, these ions right here, are being used. They're reactants. So on this copper half cell, these copper ions are actually attaching onto this anode. Sorry, that's not an anode. You're going to find out later, this is the cathode. But the copper 2 ions are going to attach onto here, so the copper 2 ions are coming out of solution. We need to replace that positive charge. So the cations, remember cation is a positive ion, so the positive ions from the salt bridge will go to the copper half cell. Zinc ions, look at this, we are making zinc ions. So we're building up positive charge over on this side. In order to neutralize that positive charge, we need to send negative ions. So anions. Anions, recall that these are the negative ions. Negative ions. So the anions flow to the zinc half cell in this particular voltaic cell. Okay, electrons. We have to look at our half reactions. If you look at the half reaction for the zinc, we reverse that. So electrons are a product for the zinc side. Oh, here we go. It's right here. Zinc makes zinc 2 plus 2 electrons. We're making electrons over on the zinc side. So they are produced at the zinc half cell and they are used at the copper half cell. Right? We need electrons over here. Electrons are a reactant on this half cell. So electrons are being made here and they're heading over to the other side. So electrons are flowing from the zinc anode to the copper cathode. Now, how did I know that zinc was the anode and copper was the cathode? Let's look at that because we didn't go over that in here. So remember an ox and a red cat. Oxidation at the anode, reduction, cathode. This is reduction, therefore copper is the cathode. This is oxidation, therefore zinc is the anode, an ox and a red cat. Okay, let's do a problem. That was just an example. You're going to do this one on your own. Actually, this is really our second problem. The first, I just always say it's an example though. So look up the aluminum half reaction and the magnesium half reaction. You should look those up here. So you're looking up the aluminum half reaction potential and the magnesium half reaction potential. You're going to fill those in, and I'm going to just uncover this. Okay, so the overall cell potential, this means the cell potential where we add the oxidation and reduction half reactions together. We need a positive number. So which of these two numbers should I reverse so that when I add them, I get a positive number? Hopefully you recognize that this is the number that when we reverse this number, change the sign and add it to the other number, we will get a positive E0. So we need to reverse the magnesium half cell. And the two half reactions, those are two half reactions. Now, you're going to identify what's going on each side, and I'm going to open this up in a moment. So reduction is where electrons are a reactant. Oxidation, electrons are a product. Al3 plus is gaining electrons because electrons are a reactant to become aluminum. Magnesium loses electrons because electrons are a product. Gaining electrons, gaining electrons is reduction. Losing electrons is oxidation. Oxidation occurs at the anode. Reduction occurs at the cathode. We have our E0s as well. This is oxidation, so I changed the sign. The oxidation is positive 2.37. And we have the cathode is where reduction occurs, and the cathode is the piece of metal, so it's solid aluminum. The anode is where oxidation occurs, an ox, and the anode is that solid metal, the magnesium. For the overall balanced reaction, notice we have 3 electrons here and only 2 here. So I need to multiply this magnesium reaction by 3 and the aluminum reaction by 2. I add those together and I get this overall balanced reaction. This is not balanced yet. I need a 3 and a 2 and a 2 and oops and a 3. And now that reaction is balanced. Okay. Number 2, a galvanic cell has a copper-2 and a silver ion half cell. Find E0. What's the balanced reaction? What's the anode? What's the cathode? Lots of questions here. All right, so first you need to look up. Oh, that's interesting. I'm not sure I had that little box there. Okay, we have to look up the reduction potentials for silver and copper, and I have a blank here, and that's also a blank here and here. I apparently repeated this twice. So look up your reduction potentials for copper 2 and for silver. And you go back to this table to look those up. Copper 2, 0.34. Silver ion, where did it go? Where's the silver ion? It's in here somewhere. I'm just not seeing it, but oh, there it is, right there. Silver is 0.80. So you're going to fill in these boxes, and you could also fill in the underlines there. All right. So now E needs to be positive. The cell potential must be positive, so you decide which of these you're going to reverse. And I just noticed I had the wrong sign on the silver. Silver is positive 0.80. So you decide which one of these to reverse, and we need to reverse the more negative half cell potential, which would be the copper side. So we're going to reverse the copper half reaction. And the two half reactions are going to be our silver half reaction. Okay. So we have our half reactions. We reverse the copper reaction. So now we have reduction and oxidation. We check whether electrons are a reactant or a product. Who's gaining, who's losing. Our cell potentials, we're going to add those together to get a cell potential of 1.14. Notice we changed the sign for the copper half reaction. And we identify from a red cat and an ox. The cathode is the silver, the anode is the copper. Balanced reaction, we need to multiply this reaction by what? We need to multiply it by 2 to get this balanced reactions. Okay, now where are the ions flowing? Let's see. Silver ions are being used. The positive charge must be replaced. So the cations from the salt bridge go to the silver side, the silver half cell. Copper 2 ions are being produced right here. So this positive charge must be neutralized by the anions from the salt bridge. And this was supposed to be covering this up. Anions flow to the copper half cell. Okay, so electrons, we have to think about the half reactions. Electrons are being used on the silver side. They're being made on the copper side. So the electrons have to flow from the copper side over to the silver side. And here is your information. All right. Cell potential, electrical work, free energy. So there's a relationship between Gibbs free energy and the cell potential. N stands for the moles of electrons transferred in the balanced reaction. F is just Faraday's constant that was listed up on the first page. So let's do a couple problems. Find the Gibbs free energy for problem 1 that I had up there. We know E0. We found that in problem 1. We have to find N. There are 3 moles of magnesium, and each mole of magnesium gives 2 moles of electrons. So 6 moles of electrons are transferred when the reaction occurs. N is 6. We plug that information in for delta G, and we get this. Next problem, what's the Gibbs free energy in problem 2? And that would be the Gibbs free energy for this problem right here. We have E0. Overall, I think it was 1.14. Where is it? There we go. It's 1.14. The moles of electrons. Well, we need 2 silver ions. You can pick any chemical. So we need 2 silver ions. So I would multiply this reaction by 2, which means I need 2 electrons. N is 2. I plug that in, and I get my delta G. 2 moles of electrons, Faraday's constant, and the voltage. Remember, a volt is a joule per coulomb. Okay, cell potentials, E0, not E0, because E0 means standard conditions. So this, notice there's no little 0 up top. It's not like this one. E is the cell potential, and we're going to look at the cell potential versus the reaction quotient. Now, these have gotten all out of in the wrong places. So your handout has them in the right place, so you'll figure that out from your handout. Understand standard conditions. Q is 1. E is E cell under standard conditions. So we have 1 point for this graph, and at equilibrium we know Q is K at equilibrium, and we have no Gibbs free energy and the cell potential drops to 0 at equilibrium. There's no energy that could be produced. So we have another point on this graph at K, 0. All right, here's what the graph should look like. Something like this, not exactly like this, where our y-axis is the cell potential and our x-axis is the reaction quotient. Now we're going to do some problems, and you'll look at this graph to figure out the problem. If we increase the Al3 plus in this reaction, we've increased a reactant, and the reactant is now greater than 1 molar. The product is still 1 molar. So Q is less than 1. Remember, Q is products over reactants. So I have 1 cubed divided by 2 squared. It's 1/4. It's less than 1. So the reaction, Q is less than 1. It's over here. So now we can look and we see our cell potential is greater. We are farther from equilibrium along this axis. And the cell potential will be larger than E0. Notice we're moving away from equilibrium is right here. When we get closer to equilibrium, the cell potential heads towards 0. Farther from equilibrium, the cell potential increases. Let's look at B. We increased the product concentration. So now Q is greater than 1. The reaction is closer to equilibrium, and the cell potential is smaller than E cell. As we move toward equilibrium, the cell potential decreases. We have something called a Nernst equation. You're not going to need to use it. But if we're at equilibrium, Q is K, E is E cell, we could plug those values in. So if Q is K and E is E cell, we have this equation. And in thermodynamics, we have a relationship between delta G, K, and E0. So now we have been able to show that thermodynamics, equilibrium, and electrochemistry all depend on each other. And that's it.